right? The second thing is to be able to identify what's the correct procedure. So to say, okay, I found this wrong. This is kind of the steps that I would do to do this correctly. Reiterating through those steps kind of brings it to mind. When I see this type of problem, do these type of steps. And then you want to follow through and do it. So that's the three things I'm looking for when I see an extra credit area that you've identified. What was your mistake? What are the steps I should take? And how should I go about it? Then ideally, I want it in your words, not somebody else's. The big thing is, if you can take a concept and you can express that concept in your own way, then that means you really own it. Right? And that's what I really care about, is that you own the ideas themselves. So I'm not as concerned with some big fancy explanation or whatever else. Don't try to tie it into somebody else's thing. That doesn't help, right? Memorizing somebody else's solution is not going to help you in the long run. So I want you to be able to bring it down, and I sometimes call it the grandparents' level of explanation. My grandma lived with us when we were growing up, and she was one of those do-anything people. She was a Rosie the Riveter in World War II. There's like nothing this woman couldn't do. But she grew up in a time period before tech. So, growing up with her, she was one of those cool influences on my life. And so I found if I could explain what I was studying in college, and she could understand it as my example of a smart person just who isn't aware of this technology, then I must know it, because I could now, conversationally explain it in a way a smart person could get it. So that's why I kind of call it the grandparent explanation level. So try to do it at that grandparent explanation level area. Because if you can explain it so that, your grandparents can get it, and they go, oh yeah, I can see what you're doing, then it's yours, right? That knowledge you will know forever. You will never forget it, because it's just part of who you are. And that means you'll be a really good designer at that point. Does that make sense? Now this will work for you as a principal. Since we're doing things, these gates and everything else, how do you break up circuits? It doesn't matter if you're analog or digital. The process of breaking up and understanding these things is universal across it. So that's the other half of it to do. Real quick also, for those who need to make up on the lab portion of the class, when you're, most people in the middle kind of need like a little bit extra time for sign off, particularly since there's only one of me in the labs right now, being able to do it. So if you need that time, please, I know you're going to come in person, but sign off and grab a WebEx time if it's during office hours. And the reason for that is if you don't, and you just show up at that time, somebody could grab the WebEx time, and then I'm double scheduled. And whoever signs up on the WebEx, they've got a reserved time. I have to take them. So it's really just a scheduling issue, right? So sign up for the WebEx whether you want the WebEx time or not, right? Just because you want that time period reserved. Does that make sense? Actually, the majority of people who have signed up for WebEx time so far with me have actually just come in person. So there have been a lot of people asking, hey, how do I get that? So if it's any of the times that I've already mentioned, you can either sign for it for WebEx if it's an office hour. I've got one of the boards in there, or at least one of the trainers, so you can just drop your board in, hook it up, and we can verify things. The other way you can do it is, if it's not one of those times, but I've said it's okay, just send me the time so I can stick it in my calendar to say that that's there. If it's outside those times, please send it to me in the Canvas. Canvas has its own little email thing. Don't use the Baylor email. The reason why I want the Canvas email is we do have a lab assistant who is using for grading and things. He can also sign off. So if I don't have time because I'm in class or something, and you send it in there, it's visible to both of us if you include both of us. So his name's Gordon Ledford. So if you include both of us and you put it in Canvas, the two of us can see who's available, and one of the two of us can say, yeah, I've got it. Does that make sense? Yeah. Yeah, so for the hour from right after this class until 12 o'clock, and it has to be 12 o'clock sharp because I'm going to meet my lovely daughter who's a freshman here, so for lunch. So I can't make her wait. But between now and noon, I have time if we want to do sign-ups. So, and like I said, it'll probably just be in my office so that we've got the trainer board there. Yeah, as long as just, at this point, for the one after, I'll just take you and first come, first serve. Nobody has specifically signed up for those that I've seen, so I'll just, first come, first serve. It's probably I can handle in about 4. It seems to be taking about 10, 15 minutes a person when I've done them so far, so I probably have enough time for about 4 after class. Yeah, that was your question. Awesome. Okay, if there's no other questions on those, then we'll start talking about lesson for the day. Will you? Awesome. Okay, so last Friday we started talking about how we can get to some of these different things. We mentioned the sum of products and the product of sum forms, and we said we want to get more specific. And we introduced the concept of a min term. I said we'll go into more detail. So today we're going to talk about min terms and the associated canonical form that goes along with them. So the first thing we want to talk about is why we have a canonical form. So to kind of introduce this concept, let me ask you a question. We've talked about kind of gate level stuff, right? And we said every equation gives us some type of a gate as a result. So let's say I had, I don't know, x or maybe xy, let's make it more, or z and x or exclusive or y. Right? So when we look at this, right, it's a fairly small equation that's in here. And we could look at this and say, okay, let's figure out how many gates it is. And we start, remember, we can either start on the left side or the right side building them. I'm going to start on the right, which means I look for whatever is the last thing you're going to do, i.e. the lowest priority. And the lowest priority of my gates is right here. So that's an OR. And it has 2 inputs, right? This is input 1, and this is input 2. So I go, okay, that OR has 2 inputs. One comes from an AND gate, so implicitly if I don't draw it, there's a dot. I've got an AND gate. That would be at the next level down. And it has 2 inputs, an X and a Y. The other input over here, again, parentheses is my highest priority, so whatever happens in here has to happen before this, so this is my next lowest priority on the other input. So again, it's an AND gate coming back. That's this next one. And it has 2 inputs, here and here. So one of them is a Z, and the other one goes back to another gate, an exclusive OR, which looks like an OR with the extra curved line. And it has an X input and Y input. Does that make sense? Now, if we look at this, we said one of the things we really care about is how long it takes for this circuit to be able to calculate things. That's how fast your circuit will respond to things. And we count the longest or slowest path through the whole system, which gives me 1, 2, 3 gates. You can kind of follow this line. This isn't removing it, I'm just kind of marking which is the slowest. And it's either one of these, it doesn't matter. All right, so we call that our critical path. It's the slowest path through the system. And it costs me 3 gates. So this circuit is going to have a latency of 3 gates. So I can ask the question then, what is the fastest system, i.e. in terms of how many gates, depth-wise, it takes to implement any circuit out there, depending on, because there's different ways, as long as I maintain the function. So this is a particular implementation, but there's other ones that have equivalent. So for any particular function, what is the shortest ones of these slow ones I can ever do, i.e. the fastest of my slow pass? Does that make sense as a question? So what do you think? Do you think is 3 as slow as I go? Can I beat 3? Can I not beat 3? I think it varies by circuit. How many people think it varies by circuit? Don't feel bad whether, right? The whole purpose of committing to something is, if your mind commits to something, whether you're right or wrong, it's going to actually help you to program it. If you discover you were right, then your brain goes, yay, and it reinforces I'm right. If you find out that you weren't correct, it goes, change it. Either way, it's going to help your brain grow. So it's irrelevant to me whether you're right or wrong. I just care that you learn the material. Okay, how many think we can beat 3 all the time? How many think the best guarantee I can make is worse than this? 3. So far I've had 2 people vote. So where's everybody else at? We got quite a few more. There's 20 some odd people here. So I got about 10% of the people who have an opinion. What do you think? Right? Rewrite a function. Right? So I could rewrite this in lots of different ways. Do you think I can rewrite this function, maintain the same basic truth table, but make this shorter? Right? So how many people think I can make this quicker? Okay, so now we're getting some more that's in. So if I can make this quicker, how much quicker? Can I make it 2 gates? 1 gate? What do you think? How many people think the best I can do is 2 gates in trying to improve this? How many people think I can get down to 1 gate? All right? So this is a non-trivial statement, but it would be interesting, isn't it? Now, most of the people are going with 2 gates, all right, as a guarantee. If I had any other function out here, do you think for some generic function, let's say f2, all right, without me specifying what the function is, do you think for any generic one I can get down to 2? How many people think for just any old function out there I can always get to 2 gates deep? How many people think I can at least get to 3 gates deep for any other old function out there? Any function. Any Boolean, I can make any combination of gates I want, any truth table I want. The slowest path, can I make a lower bound guarantee? How, what's the worst I'm going to do? That make sense as a goal? So how many people think it's 2? How many think 3? How many people think you have no way of knowing? It could be anything. Few people, right? So most people think it's 3 or maybe unknowable. Pretty much almost nobody went with 2. Would it shock you if I said I can guarantee I can do it in 2 gates or less no matter what the function is? Would that be shocking? Is it true? It's true. You never have to go beyond 2 gates deep. We sometimes do to make the circuit simpler for ourselves, right? So conceptually it might be a little easier for us to deal with. But this is why we do the canonical forms. If you write them in the canonical form version, you are guaranteed to be able to get it in 2 gates or less. And on top of it, you'll not only get 2 gates or less deep, but you'll be able to design it with only 1 gate type. That's probably even more shocking on top. So I can guarantee that I can get a really fast system, and I'll only need to use 1 type of gate. Up till now, you've had to deal with ands and ors and swap some XORs in and things like that. We're only going to need to use 1 of 2 types of gates. We're going to have 2 basic canonical forms. Each canonical form is going to have a gate type. That's kind of a shocking thing, right? If you think about what the meaning of canonical forms is. Now, the other reason we would only need 1 type of gate, yeah. So we could actually reduce this in the type of gates and the speed. Now, when you do this reduction, like right now, you can say things like, this is a half adder. This little section of the circuit adds these 2 bits together. And when you break it up into the canonical forms, it's not going to have that intuition anymore. So you always pay something, right? There's a trade-off in all of life. If it wasn't, engineering wouldn't exist. So you can't have everything you want, so you have to pick what's important. That's really what engineering is all about. We call it the waterbed effect. I make something better, I'm going to make something worse. So you have to pick what are the better things that matter. So you can pick those and you say, which ones can I tolerate something getting worse on? So for us, usually gate simplicity and things like latency, speed are very important issues. So that's why these canonical forms are very nice for us. Okay? The design you did on this one was very easy to understand, at least at the beginning, because you could say, you're building a circuit that kind of mimics the way a human being thinks. That was the design in lab. And we did that, number 1, so you could see that technique. But number 2, you notice it's kind of slower, it gets kind of uglier. It doesn't scale nicely like this does. But you also don't need the techniques we're going to have to build to use these. Life's a trade-off. Make sense? Okay, so let's develop why I made that statement. So if I make a statement to you that sounds kind of shocking, you can do it in 2 gates or less, I should have to prove it. Okay? So here's my first step. Any old function. Since I'm going to deal with any old function, I'm just going to call it f. And that just helps me to not have to write something extra every single time. It's just laziness. Okay? Do we agree that any function can be written as a truth table? So if I have function, I'm going to put in parentheses here, say x, y, z. This is whatever the inputs are to my system. So if I've got, in this case, 3 inputs named x, y, z, I can label them x, y, z. This will just tell you how many. And it doesn't matter how many variables it is, and I'll show you why in a sec. I will also sometimes write this as f underscore x, y, comma, z, or just f, x, y, z. And when I'm typing, I'll often do that underscore. And the reason is that's the LaTeX version to tell me that it's a sub thing. But it's sometimes easier to type that or to write that just because they stay bigger. The subset here just makes it nice. I don't have to use the parentheses all the time. It's sometimes a little easier to read when you're going through them. But all these are going to mean the same thing to me. Now, do we all agree that for this, I can write it as a truth table? X, Y, Z, the inputs. And I could have my function f of x, y, z. And I can write this as a truth table. Do we agree that's true? No matter what the function is? So my x, y, z is going to look like 0s, 1s, 0s. And I will have some combination of 0s or 1s here. For lack of anything better, it's okay if I just pick 0, 1, 1, 0, 1, 1, 0, 0. Is that fair? I just literally wrote down. I did this actually so that I have a bunch of different styles, right? A 0 and a 1 and a 0, both ones, both zeros. I just picked it so you had all possible combinations within a sets of 2. There's nothing magic about the sets of 2 here. I could just walk through those particular ones and grab them all. All right. Now, if you remember last time I said we could write what we were going to call min terms. And what a min term is we're going to have these new little functions, m, let's say for instance 0. And m0 was going to be the min term on this first line. Actually, I should write up here. And we want our min term to be true in the case when I'm on line 0. So I just read this as a binary number 0. Min term 0 should be 1 there, and it should be 0 everywhere else. Does that make sense? That's just how I'm going to define it. So any min term I want, right, if I want to define min term 1, it would be a 1. When I just treat this as a number, I say in binary, 1 is 0, 0, 1. So I put a 1 there. Everywhere else, it's a 0. Good? So let me ask you, for instance, what would min term 5 look like? So I take a look, yes. So let me just show why though, right? 5 in binary is 1, 0, 1. So I find this 1, 0, 1 pattern on my inputs, and I put a 1 there on the output. And everywhere else, I'm going to put zeros. All right, so I'd have 0, 0, 0, 0, 0, 1, 0, 0. So whatever that number is there, turn it into binary, find that on your inputs, and go. This is the second reason that these are important. This is not the same as f, y, x, z. Not the same. And the reason why it's not the same is I have to be able to read these in order. So if you swap 2 of your variables, that means you'd be swapping 2 of the columns. So the min terms wouldn't be the same. So order matters in the list. Is that good? That's the big thing I'm getting out of these. Notice every single time I wrote it X, Y, Z. Because order matters. Because when I take these numbers, order matters when I write the binary digits. Which one's most? What's the middle? What's the least? Okay. So let me ask you, what min terms can you see making this one up? If I were to just walk through and grab each of these, I'd kind of have this one and this one. It looks like I don't have enough colors. I'll have to use red also. Sorry, I only have 4 color pens. So if I were to look at this, so let's say, M0. We'll take that one. So the function f of x, y, z. When I write this, I can take it, the blue min term here, this one, is 0, 0, 1, so that's little m1. Right? That would give me a 1 right there. If I looked at this next one that I circled with my black pen, what min term would that be? M2. How about the one I circled with my green? It's M4. And the one I circled with my red pen, that's M5. Now, that gives me these possible shapes, right? And I want to combine them, and if there's a 1 anywhere, I want to keep the 1s. But I don't want to keep the 0s. What gate lets me do that? It keeps the 1s, but it doesn't keep the 0s. It's an OR. Exactly. So if I took this, I'm just going to use green because I think it's a little easier to read for me. If I just ORed all these terms together, do we agree that this would give me that? Now, I can list where all of the 1s are by just listing all the min terms, right? And if I OR all of my min terms, doesn't matter how many of them there are, if I OR them all together, I can create something that is at least output-wise identical to the function. The question is, how many gate levels does it take to implement these min terms? Because I've got 1 gate level to combine them together. If I can do these min terms in a single gate, then I'd have 1 gate level, 2 gate levels done. And we just showed we could do it for anything. Does that make sense? So this would guarantee me 2 gate levels. I just literally write it as a sum of these min terms. This is what's called a constructive proof. I'm showing you I can build it for any function. Once you know how to build it for any function, it's proven you can do that, so therefore it must be true. I can do it in 2 gate levels. All right. So the question is, how do I build these individual gates? So if I wanted to get something that's true only in one spot, what type of a gate gives me a true only in one location and everywhere else it's 0? So an exclusive OR is going to be true, which is circle plus. If I take, for instance, let's say A and B, and the exclusive OR of A and B, right, is if they're ever different, it's a 1, and if they're the same, or whether it's a 0 or a 1, they're not. So exclusive OR is going to be half of the time true and half of the time false. So exclusive OR, and it doesn't matter, if I were to negate one of these terms, it would just flip those pattern areas, but you're always going to have half the time on, half the time off. So it's good to start kind of recognizing these patterns. Right? So don't feel bad about taking those guesses on what it could be. Right? The important thing is you start seeing, when do these gates happen? So if you read the book, they actually talk about there's a ton of different gate names. I could care less about all the gate names. There's actually some families. So exclusive OR in its family is basically right half the time. There's another big family that's going to be right all the times but 1, or true all the times but 1, and there's going to be another big family set that's going to be right once and wrong all the other times. So this is 50-50. So that's not going to meet our true only once. What do you think? What's another potential type of gate? And. So how does AND work? If I tried A and B, all right, what would I get? 0, 0, 0, 1. Now, it always has that 1 in the last spot. Does that really matter? No, because imagine I could just negate some of these. So for instance, if I wanted in the first spot, I just had to turn this 0 into 1 and this 0 into a 1. So what if I just did A prime and B prime? I primed both of them. So A prime is going to look like 1, 1, 0, 0. And B prime is going to look like 1, 0, 1, 0. So A prime and B prime will be true when A and B are both 0, which means when I'm ANDing them, I'll get a 1, 0, 0, 0. That make sense? So AND gates are only going to be true once. They will only be right one at a time. So all these minterms are AND gates. Right? They'll have certain negations in them and stuff like that, but we don't care about the negations. Gate-wise, it means it's a type of AND gate. Does that make sense? So that means all my minterms can be written as AND gates. So the M0 is going to do something like this. I have to negate the inputs. So if I were to look at M0 for this X, Y, and Z, and we go back to red because that's what I'm using here. So let me take this midterm here. I have to have X, Y, and Z. And we said in the 0 position, I need all of these to really be 1s as inputs. So if I knotted all of these, they would all become 1s, wouldn't they? So that means I have to knot the X, I have to knot the Y, I have to knot the Z. That'll make them all 1s when X, Y, and Z are all 0s. And if I then AND all those 1s together, this will now be true when X, Y, and Z are false. And since it's an AND gate, it can only be true one time. So all the other cases must be 0. Does that make sense? Now notice, whenever it's a prime, I get a 0. 0, 0, 0, which is binary for this. Let's consider 0, 0, 0, 1. If I want a 1 here with an AND gate, so M1, I know it's got to be X, Y, and Z. We said we're going to want an AND gate. And then I want the inputs to be all 1s. So which ones am I going to have to negate? I can't have a 0 on this line, can I? So I better negate that X, right? Because if I negate X, it'll turn the 0 to a 1 and any 1 to a 0. So if I negate X, this would become a 1. What else do I need to negate? Also need to negate Y. Do I need to negate Z? No, it's already a 1. Right? So if I consider X prime and Y prime and Z, it'll be all 1s as an input here. And then I AND them together. When your inputs are all 1 to an AND gate, you get a 1 as an output. Any other case, it doesn't. So this has to implement it. And notice again, if it's prime, it's a 0. If it's not primed, it's a 1. 0, 0, 1 gives me this. That make sense? So let me ask one other kind of interesting question. Let's say I consider this M5. Notice a pattern forming here? Anybody take a guess what M5 should look like? And Y prime and Z. Because X will give me a 1, X will give me a 0, and 1. Right? When X is a 1, when Y is a 0, Y prime will be 1. And when Z is a 1, it's 1, so I'll have all 1s on input. And conspicuously, that is the number 5, and that is true. Any other case, it's a 0, so this has to give me that. So if you notice, every single one of these minterms can be written as a single AND gate. Multiple inputs, but a single AND gate. Therefore, this function, f of x, y, and z, can then be written M1 is going to be x prime, I'm not going to put the dots in anymore, y prime z, 0, 0, 1, and 2, that's x y prime z, 0, 1, 0. Sorry, I just did that backwards. Yeah. Yeah, let me scribble it out in a different color. Right? 0, 1, 0, 2. Sorry, I am dyslexic. I do sometimes write things exactly backwards. But it's a good thing to be able to check, right, if you know the pattern to them. 4, right, means the first one has to be a 1, and the other two are zeros. Y prime z prime. That gives me 1, 0, 0. That's 4. And then 5 will be 1, and then 0, 1. 1, 0, 1, that's 5. So if you notice, I have now been able to write this function as a single gate. And it didn't matter what the pattern was. So I could, in theory, take any old function I want, make its truth table out, read out every single time there's a 1 in the function. I just make a list of those min terms, and then write out what the min terms are described as, and I get a 2-level gate implementation. Since I could do it for any truth table, and everyone has a truth table, and it's unique, or at least for that right? I shouldn't say it's unique because there's several different ones that do it, right? Anyone does have a truth table, though. That means I can write any of them in this form. Question? Or is that? No. Okay. So do we now agree this? That means you've just proven you can do anything you want in 2 gate levels. That was the first half of my somewhat shocking statement that we've been able to prove. So since we have a constructive argument to build it, it's true. Let's see if we can draw the circuit for this. So I'm going to copy this function over, so I'm at the top. F of x, y, z equals x prime, y prime, z, or x prime, y, z prime, or x, y prime, z prime, or x, y prime, z. Okay, so I just copied it. Hopefully I copied it correctly. So we'll start off with this. Now we want to see everything generates a picture, right? A circuit for us. Our final gate is this OR. So this is a 4-input OR gate. Here's first input, second input, third input, fourth input. So that means I need a pretty big OR. So I can now introduce another convention. I don't want to draw 4 tiny little lines in here, but I don't also want to make this gate retardedly huge, right? I want to keep it at a reasonable size. So we can also extend the lines out. For ones that have curve, we extend the sides out with another curve. If it's an AND gate, that's a straight line, we just extend the straight line out. So that allows you to keep your gate at a reasonable size, but I can allow for more inputs. We never put an input right on these kind of corner areas because it's really hard to read whether you're trying to mean as part of the line or not. So I can now kind of break it into 4 pieces. So I've got 4 different ones. First, second, third, fourth. First, second, third, fourth. You should keep them in order. All right? Not that it technically is wrong as a circuit if it's not, but it's very hard to check if it's not. So if you have a consistent pattern, you're going to make it a lot easier on you and whoever has to verify your circuit. So this is an AND gate, and that input is 3 inputs, right? So I've got technically an AND gate here. So first input, second input, third input. And we can now go in here and go, this is, I'm going to take X, and you either are going to use X or you're going to use X prime. So since I'm going to do a whole bunch of these, I'm going to start making just easy available for me so I don't have to mess with it, both the regular and the primed version. So this is y and y prime. This is x and x prime. Make sense? It just makes them available. Then I can just draw whichever line I want to connect them up. That gives me z and z prime. Okay, so I want x prime, and I want y prime, and I want z. If it's 3, I'll stretch it to kind of fit in. If I get to 4, I'll probably draw the sidelines. Okay, so far so good? Help me out with the next one. How do I draw that? I'm going to need another AND gate and need this x prime, right? And I need my y. And I need z prime. We agree? The next one, that's this. So we can call this kind of gate 1, 2, 3, 4. This is 1, 2, 3. I'll have a 4 down here. So 3 needs x and needs y prime. And it needs z prime. And 4 needs x. That's x. And it needs y prime. Got this y prime already coming over. And it needs z. We agree? Now right now, I've got 2 different types of gates, right? An AND and an OR. But I told you you could do it with 1 gate type. So I've proven half of this to you. You can do it at 2 gate levels, but I haven't proved the second half. Okay? So I'm going to take this. And there's 2 gates that we're going to call universal gates. So our 2 gate types are going to turn out to be NAND and NOR. I'm going to back into these to show you why I say they're universal. But I'm going to start by just telling you, hey, these are the 2 ones we're going to use. And I'm going to start with NAND here because that's going to turn out to be useful to me. So I'm going to consider these AND gates. I want to turn this AND into a NAND. How can I turn an AND into a NAND? Yeah, I need to have a negation. But if I'm going to negate this one, doesn't that change the circuit? So how can I not negate this or not change the circuit? Remember, every trick that we're going to do is either going to come by ANDing it with 1 or ORing it with 0, right? So to AND it with 1, I could just double negate, couldn't I? If I negated and then negated, it would basically undo itself. Do we agree? And we said if we drew a bubble, it would negate it. So if I did 2 bubbles, it would negate it and then negate it again. Yes? So I haven't changed anything, but now I've negated 1. Let me do that same thing every time. So far, so good? All right. These are all now NAND gates. So I go at this level, I'm done. At this level, what I've got is an OR gate with negated inputs. And all of them are negated because I have no choice. With this canonical form, it has to all have them negated. So let me just, for simplicity's sake, I was using XYZ here. I could call this wire between here A if I wanted, and B, C, D. Does that make sense? So if I call this A and B just for a smaller case, this is the same as, say, A prime or B prime. Do we agree? This kind of looks like a De Morgan's thing, doesn't it? Because I don't want an OR, I want an AND. So I need to flip gate types. The one thing that lets me flip gate types is, remember I said we have our good old friend De Morgan's, and De Morgan's is going to be very helpful to us all the time. It's about to help you again. What does De Morgan say? Remember I gave you kind of my colloquial version of it, which was flip or negate the inputs, which in my case, negating A prime gives me A, negating B prime gives me B. So I negate the gate types, I switch the gate, it becomes an and I negate the output. So therefore that means I've now got my A and my B coming in, and these are exactly identical. It's coming in into an AND gate, and I've got a negated output. So if I have an OR gate with all the inputs negated, but not the output negated, it is exactly the same as an AND gate without the inputs negated, but the output negated. Well, that's what I have here, right? All the inputs are negated, but the output isn't. So that means this is the equivalent of replacing it with an AND gate with the output. So therefore this can be rewritten as X and Y and Z these come into our gates. 1, 2, 3, and 4. And that one goes there. And it also comes here. I'm just going to try to copy my wires. And X. Goes to the bottom too. And we need Y prime to the top and the third. Y prime to the top to the third. That means Y has to go to the fourth and the second. Oops, no, Y prime should go here. Bad me. Oops. Sorry, I misread my lines, right? So Y has to go to 2, but that's it. And Y prime goes to 1 and 3 and 4. Okay. And let's see, I need my blue pen. Let's see. And then Z negates